This lecture is going to go over the concept of ionic bonding, which starts chapter 4 of the OpenStax textbook. And so when you think about bonding, we have to answer a couple questions. And some of the questions we can start to answer is, first of all, what is a chemical bond? Why are some materials soft and flexible while others hard and brittle? Why is something like hydrochloric acid, HCl, a gas, but a very similar molecule, at least in how it looks, sodium chloride, is a solid at room temperature? And we can start to answer all these questions when we start to address chemical bonding. And really, an understanding of chemical bonding is really the gateway to sort of understanding how to solve a lot of the problems or areas of research of the world today. Things like energy, pollution, disease, food, all of this, if you really want to understand it on a chemical level, you need to understand bonding. And we've seen in one of the central themes of this course, and in particular this chapter, is how does molecular structure affect reactivity? And we're seeing a real live example of this in the world right now with the coronavirus and those spike proteins, right? That spike protein structure is affecting reactivity. And that's really the focus of this whole chapter. How does structure affect reactivity? So we'll start off with the basics and talk about chemical bonding. So at its simplest form, a bond is just a force that holds atoms together. And one of the things to take away right now and mark in your notes is that the bond is a force of attraction. So anytime you want to break a bond, you have to put in energy to break apart the atoms. So breaking bonds always requires energy. And if you're forming a bond, that will always release energy. Now, there's a couple different types of bonds, and we're going to go over each. There's a covalent bond, and this is where an electron pair, so two electrons, are shared between nuclei. We have an ionic bond, which is a force of attraction between a positively charged cation and negatively charged anion. And then we have a metallic bond, in which electrons are actually shared between many metal atoms. So instead of shared between two atoms, they're shared between a lot of atoms. This lecture is going to focus on ionic bonding. And then the next lecture, we'll talk about covalent and touch upon metallic bonding. So the first thing to think about with an ionic bond, right? So these are molecules that are held together through the attraction of again, cation and anion, a positively charged and a negatively charged. So all it is a force of attraction between a positive and negative charge. Just think about magnets. Almost all of chemical bonding, we can use this analogy of a magnet. Opposite charges attract. And so when we think about this, we have to understand what elements on the periodic table are going to form cations and what atoms on the periodic table are going to form anions, right? Where are the elements that are going to lose electrons to form a cation, and where are the elements that are going to gain electrons to form anions? And we started to talk about this when discussing the periodic table and ionization energy and electron affinity, but we can look at this a little bit more detail now. And some things to keep in mind as you look at the periodic table. Remember, group 1, the alkali metals, these will always form a cation and they will always form a positive 1 charge. And that's because they have 1 valence electron. So alkali metals will always be +1. Alkaline earth metals will always form the cation with a positive 2 charge because they have 2 valence electrons that's weakly held. And so when they form a cation, they're going to lose both of those ions, both of those electrons to form a positively 2 charged cation. Jumping to the other side of the periodic table, we can see the halogens, right? So group 17 or 7A, these are always going to form an anion. They're always going to gain electrons because of the high Z effective. And they only have spot for 1 electron based on their electron configuration. So a halogen will always form a negatively 1 charged anion. Group 16 or 6A will then always form a 2- charge. And we can start to see some other things that we also have these transition metals, right? So this is our transition metal block right in the middle of the periodic table. And these are a little bit more complicated, because a lot of these can take up more than one charge. And so we're going to have to learn how to specify that and determine that. There are some exceptions. Things like silver will always be +1, zinc will be +2. You don't need to memorize these things. What you should know are the charges of the alkali metals, alkaline earth, and the charges of the halogens. Those you should definitely know what charges they will be. So the next question then becomes, how do we know if we're going to have an ionically bonded compound or a covalently bonded compound? And really the key for this is an ionic compound will always be formed between a metal and a nonmetal because we need a cation and an anion. So anytime you have an ionically bonded compound, you're always going to have one of the atoms be from an element that's a metal, the left-hand side of the periodic table, and the other atom is going to be a nonmetal, the right-hand side of the periodic table. Watch out for hydrogen. I've color-coded it blue. While it shows up in group 1, it's really more thought of a nonmetal over here. So a covalently bonded compound is always between two atoms or more that are all nonmetals. So covalently bonded compounds come from our nonmetal side, and then ionically bonded compounds come from a metal and a nonmetal. Within our ionically bonded compounds, we need to be able to draw molecular formulas. And so if we look at something like, what is the chemical formula of magnesium chloride? And then we'll say, what is the chemical formula of copper 1 bromide? The key for both of these is when we think about our chemical formula, we have to think about what the charge of our two ions will be. So magnesium is a alkaline earth, chloride is a halogen. So we can see magnesium is going to form the charge +2, and chloride is going to form the charge -1. And the key is of any ionic solid, the total charge is always 0. Now, we see that magnesium is a +2 charge and the chlorine is a -1 charge. So the only way we can get the overall charge of magnesium chloride to be 0 is we need 2 chlorides for every magnesium. And so our overall formula has to be MgCl2. We have a +2 and we have 2 ions that each have a -1 charge to make a total charge of 0. We need 2 chloride ions to balance out the charge of 1 Mg2+ cation. Ionic solids always have a neutral molecular formula. In our second example, we have what is the chemical formula of copper 1 bromide. A later lecture will deal with nomenclature and how we name things. But copper is a transition metal, and this is one of the metals we said could have multiple charges. So anytime you see this nomenclature, copper 1, this number in parentheses is telling you the charge of the metal. That's not needed in our top example, magnesium, because magnesium can only ever have one charge because it's an alkaline earth metal. Copper, being a transition metal, can have more than one charge, and so we have to indicate that to others. So this is copper 1. That tells us copper is a +1 charge. Bromide is a halogen, so it can only ever have a -1 charge. So the overall formula of copper 1 bromide is CuBr, 1 copper, 1 bromide, because +1 and -1 make 0, and we have our neutral copper 1 bromide. Now, when we think about ionic compounds, and we want to think more about this ionic bond, right, this force of attraction between a positively charged cation and a negatively charged anion. We can look at an example like table salt. And salt is a generic term that really is just referring to ionic compound. So all of these ionic compounds are salt, although we often commonly just use the word salt for table salt, which is sodium chloride. So if we imagine reacting a sodium atom with a chlorine atom, right, we can end up forming the sodium chloride ionic solid, Na+Cl-. And this reaction, if you perform this reaction, And I encourage you to go to this YouTube link down here and watch this video showing it. It's a pretty spectacular reaction that releases a ton of energy, right? And so the question is, what is the driving force of this reaction? Where is this energy coming from when we react a sodium and a chlorine to form this sodium chloride solid? Right? What is the driving force of this reaction? And we'll talk about that in a second, because what that's getting at is really how strong is this force of attraction between the sodium and the chloride. But a little bit more about the structure. So here's a crystal of sodium chloride. So this is table salt. It's a nice picture of table salt and a crystalline solid. And if you look at sodium chloride at the molecular level, while we call it sodium chloride, one sodium, one chloride, what we really see in reality is it's not one sodium and one chloride, but it's a ratio of 1 to 1. And the sodium chloride itself is this repeating pattern of negative, positive, negative, positive, negative, positive, negative, positive, negative, positive, right? It's this what we call crystal lattice, right? That extends in 3 dimensions in all directions. And in this case, we can see the ratio of the number of sodiums to the number of chlorides is always 1 to 1, right? That's where this ratio comes from of our sodium chloride. But in reality, it's this, this network of ions coming out in 3 dimensions. All right, so let's get back to the energetics involved here. So why does an ionic compound form? Another way of asking that is, what forces hold these molecules together, or why don't they just fall apart? And so if we go back to this reaction, sodium plus chlorine forms sodium chloride solid. So now we have our ionic solid, and in this case, we have a cation and our anion. So what actually has to happen here? Well, if we think about this process, what needs to happen is our sodium has to lose an electron, and our chlorine has to gain an electron. Well, sodium losing an electron, this is a reaction we've looked at before. That is the ionization energy of sodium, right? So it takes energy to remove an electron from sodium, right? This electron is held onto the sodium by a positive 1 Z effective. So if we want to remove it, we have to put in energy. If we're adding an electron to chlorine, that is going to release energy, and this is known as the electron affinity, right? So how strongly chlorine attracts an electron. And this is a negative energy because energy is being released. And in this case, it's negative 348. This is the electron affinity of chlorine. If we were to add these two energies together, we end up with a positive 147.2 kilojoules per mole. Now, energy being positive means that this reaction requires energy. And yet, if you go back and watch that YouTube clip, you will see very clearly that this reaction releases a ton of energy. So we're missing something. This is not the full picture of what's going on here. There must be another energy that's present, and it has to be a force of attraction, right? Because forces of attraction will always release energy when we form them. So what is that force of attraction? And what that is what's known as the lattice energy. All right, so if we go back to this picture of our crystal lattice, so here's another picture of our positive, negative ions. We look at this and we start to really examine it. One of the things to think about is if you have a network like this of positive charges and negative charges all close together, what you're going to see is there's going to be a lot of forces of attraction. So here's a force of attraction. Use a different color here. Here's a force of attraction, right? Here would be a force of attraction between any oppositely charged ions. These are all forces of attraction. But you are also going to have forces of repulsion. So a positive and positive repel each other, a negative and negative repel each other. So in this crystal structure, there are forces that attract each other, and there are forces that repel each other. The question then becomes, which force is stronger? And if you've taken physics, you might remember Coulombs Law. We're not going to use any calculations with this, but what this equation is saying is an energy related to either a force of attraction, if it's a negative energy, or a force of repulsion, if it's a positive energy, is proportional to the size of the charges. So these are the size of our ions, +1 and -1, and inversely proportional to the distance. So what this is really saying is, as the two charges get bigger, the energy goes up, and as they get closer together, the energy goes up. So when we look at our lattice, one of the things we see is that we can compare what is a bigger energy, the attractive energies, shown in red, or the repulsive energies, shown in blue. And we can rationalize this in two ways. First, we might rationalize it in saying the attractive energies have to be bigger. Why? Because table salt exists. If the attractive energies were not bigger, then table salt would just blow apart and separate into the ions. That doesn't happen, so this attractive energy must be greater than the repulsive energy. Now, why is that? It ends up being because of this R term. If you think about this alternating positive-negative network, it turns out that the oppositely charged particles are closer together than the same charged particles. Right, so this negative and negative, this is a further apart, thus a weaker force than these two being right adjacent to each other. And so for that reason, the attractive forces will be higher in energy than the repulsion forces. So our key point of this, and the key takeaway of this lattice energy, is basically the larger the size of the charges, or the closer together the ions, the harder it is to break the bond. Right? And lattice energy is a measure of how much energy it takes to break apart the ions. So the bigger the charges, or the closer together, the more energy it takes to break things apart. Let's look at two examples. Which ionic solid will have the greater lattice energy? In other words, which ionic solid in each pair will be harder to break apart? So in the first case, we have lithium fluoride or potassium fluoride. And we can see here the anion, fluoride, is the same. So we're really comparing lithium or potassium. And the way we have to answer this is we have to think about charge and size. So first we can say, well, what are the charges? Well, lithium, go to the periodic table, is an alkali metal, so that's +1. Fluorine is a halogen, that's -1. Potassium is an alkali metal, +1. And fluorine is a halogen, -1. So all of our charges are +1, -1. So the difference here is not in charge, but it must be size. And so we have to consider what is bigger, lithium or potassium? And this comes from our periodic trends. And we have to say, in this case, potassium is bigger than lithium. And that's really the key here. Potassium is bigger than lithium. Because potassium is larger, the ions between potassium and fluoride will be further apart than they will in lithium fluoride. If these are further apart, it makes it easier to break apart. The two magnets are farther apart from each other, so it's easier to separate them than it is from two magnets that are right next to each other. So we would then say lithium fluoride has the greater lattice energy. It's harder to break apart lithium fluoride. In our second example, we now have beryllium fluoride or lithium fluoride. And so here, as we compare, we can say, if we start off with size this time, we might say beryllium and lithium are right next to each other on the periodic table in the same row. So these have the same size, or close enough that size is not going to be the key. So what is different here? Lithium, we said, lithium we said is a +1 charge, and beryllium is a +2 charge. And so in this case, the key is charge. The difference must be the charge of the ions. Beryllium has a +2, lithium has a +1. So what that tells us is it's going to be much harder to break apart the beryllium fluoride because of the higher charge. The higher force of attraction of the +2 ion is going to be what makes it harder to break apart the beryllium fluoride. So that gives us our overview of our ionic solids. To sort of recap everything, we said bonds are forces that hold atoms together. Covalent bonds are electron pairs shared. Ionic bonds are force of attractions. We said ionic compounds are really three-dimensional lattices of repeating ions. And we said lattice energy is the amount of energy needed to separate the ions, and the amount of lattice energy is proportional to the size of the charges and inversely proportional to the distance between the charges. Thank you.